Alright, so in this video we go over section 5.4, the graph of a rational function. Alright, so in this section we are going to be given a function. We're going to do a few operations to write it in a simplified form maybe, we are going to use that function, that form, to find asymptotes, intercepts, everything out of the function. However, before going over the actual examples, we need to discuss a little bit about the end behavior of a rational function. And I'm going to show you how to do that in the graphing calculator with really basic examples. So we're going to go to our y function, and I'm going to graph the very basic rational function, which is 1 over x. Okay, 1 over x and x right here, and I'm going to click graph. So notice two interesting things about this function. Number one, well, it has a vertical asymptote, which is precisely the y-axis. That the vertical asymptote is x equals 0, and it also has a horizontal asymptote, which is y equal to 0. Now, by end behavior, we're going to look at the behavior around each of the asymptotes of a rational function. For example, we're going to study the behavior of the behavior of the function around the vertical asymptote x equals 0. So for example, if we approach to x equals 0 from the left, the graph is going to go to negative infinity. However, approaching to the x value, that is the vertical asymptote, but from the right, it's going to go to positive infinity. All right. Now, let's look at other cases. This is going to happen the same. Well, may not be the same. What if I had x squared, for example? How is the graph going to change? So as opposed to the previous graph, instead of having this one pointing down to negative infinity, this is now pointing up to positive infinity. So from either side, we approach the x value, that is the vertical asymptote. In both cases, we go to positive infinity. Let's look at another case. What happens with 1 over x cubed? So with 1 over x cubed, once again, we have approaching to different infinities from either side, as opposed to the previous one. What if I go 1 over x to the fourth? Once again, it goes both towards the same positive infinity. So one thing we might want to discuss here is, well, if the exponent of the, or rather the multiplicity, if you will, of the asymptote is even, then the graph is going to point towards the same infinity, as opposed to the case in which the multiplicity of the vertical asymptote, if it's odd, we get opposite directions of infinity when approaching the vertical asymptote. Now, how can we analyze this? Well, what if we shift these asymptotes? What if I have 1 over, I don't know, x minus 2, okay, 1 over x minus 2. So in this case, the minus 2 will shift to unit to the right. So that means we're going to have the vertical asymptote at x equals to 2. Let's verify that using the calculator. And indeed, it is the case. Okay, indeed, that's the case. So in this case, if we approach 2 from the left, we get to negative infinity as opposed to the right. What if I have this, but now squared? Very similar behavior with the even powers, but in this case, it's going to be towards the same infinity. All right, so we're going to do a lot of this before that's why we needed to prep a little bit with this in order to get a good understanding and put this together with what we are going to do in this section. All right, so let's quit. A second, quit. I'm going to turn this off. So let's get to the actual example. So we're going to have the rational function x minus 1 divided by x minus 1, x squared minus 4. Letter A, if needed, write it as a single rational expression. That's already given. And then factor the numerator and denominator of the function. In other words, factor everything out. So r of x, in this case, the numerator is already in factored form. And then x plus 2 times x minus 2 will be the factor form of the denominator. From this, we are going to we're going to find the domain. Keep in mind that for rational functions, you want to make sure that this is that the denominators is not 0. So we set each factor equal to 0. X plus 2 equals to 0 and x minus 2 equals to 0. That means x equals negative 2 on the one hand and x equals 2 on the other hand. Okay, again, if you want to use this bubble approach, negative 2, positive 2. Okay, so the function is only good for all real numbers except for the open bubbles. Okay, so writing this using interval notation, we get negative infinity to negative 2, union negative 2 to positive 2, union 2, that's a 2, looks like a 1, positive infinity. So this is using interval notation. Keep in mind that we may need set notation. X cannot be negative 2 comma 2. That's the MyMATLAB notation. You separate these numbers by commas. Okay, so letter C. Write r of x in lowest terms if applicable. That is if we had common factors to divide out. So in this case, not applicable in this case. Find intercepts. Recall that to find x intercepts, we need to set the function equal to 0 and solve for x, solve the equation for x. So I'm going to write this x minus 1 divided by x plus 2 times x minus 2. Set it equal to 0 and I'm going to solve this equation for x. So that is, I'm going to multiply x plus 2, x minus 2, multiply both sides by the LCD. Over here, these guys are going to get canceled. And 0 times whatever quantity is going to be 0, which will lead us to x minus 1 equals to 0. So x equals 1 is the x-intercept. Now, to find the y-intercept, all we do is plug in x equals 0, and then simplify. So I'm gonna bring back the original function. R of x equals x minus 1 divided by x squared minus 4. So for this y-intercept rather, y-intercept, I'm gonna plug in 0 here. R of 0 equals 0 minus 1 over 0 squared minus 4. So in this case, substitute 0, 0, 0 squared. And I'm going to be left with 0 minus 1, which is negative 1. And 0 squared, which is 0. Minus 4, that's a negative 4. That's going to give me positive 1/4. So y equals 1/4 will be the y-intercept. All right, determine the behavior of the graph around any of the intercepts. So again, well, actually in this case it's only the x-intercepts, right? Because we want to know whether the graph will cross the x-axis or touch the x-axis. Well, at least we know that a graph will only, well, the graph of a function will only cross the y-axis. It's not possible that it only touches, because if it only touches, that means it will work as a turning point, and then we will have two y's for the same x, so that's not going to be a function. So, all right, so let's see. So near the only one x-intercept, Keep in mind that just the same way we did it with the polynomial functions, substitute everywhere except where it makes it 0. So I have the original function here. So I'm going to use the factor form, in fact, x minus 1, x minus 2, x plus 2. And I'm going to plug in one everywhere except where it gives me a 0. That's exactly what we did with polynomial functions to determine if it's going to cross the x-axis in the form of a line with a positive slope or with a negative slope, or if it's going to touch the graph. If it's going to touch the x-axis in the form of a parabola. Remember those cases? So you want to read, if you want, just go back to that video for section, I believe it was for section 5.2, it was graph of a polynomial. Okay, so let's get 1 minus 2, that's a negative 1, times 1 plus 2 times 3, x minus 1. So we're going to have a negative 1/3 x minus 1, which is negative 1/3 x plus 1/3. So that means the graph will cross the axis in the form of a straight line with a negative slope. Okay, let's move to the next page to see what they're asking us for. So determine the vertical asymptotes and holes if they exist. Okay, so keep in mind that the vertical asymptotes are exactly the values of x for which the function is undefined, or the values of x that we exclude from the domain. Again, let me write it down. Let me write the factored form of the function, that is x plus 2 and x minus 2 under x minus 1. Okay, so vertical asymptotes, recall that they come from the denominator. Okay, vertical asymptotes. For vertical asymptotes, we get x equals negative 2. Again, these are not just negative 2, but actually vertical asymptote is a line. It's a vertical line described by a dashed line, and it's represented by a dashed line, and it's described by an equation. All right. Determine the behavior of the graph on either side of any vertical asymptote. So this is what I'm going to do. I'm going to write the function in a slightly different way. R of x equals, this is going to be the same, this function that I have here in factor form is the same as saying 1 over x plus 2 times 1 over x minus 2 times x minus 1. That's the numerator. So in this case, we are going to analyze either side of vertical asymptotes. Okay, so this one gives rise to the vertical asymptote x equals negative 2. So around x equals negative 2. So keep in mind, look at the multiplicity. Remember what we did at the beginning of the video. This is like having x plus 2 to the first power. It's an odd power. So when we graph this one, when we graph this little guy, we're going to have our vertical asymptote at x equals negative 2. And the portion of the graph is going to look like this. So what happens if we approach negative 2? From the left, we're going to go to negative infinity. And if we approach from the right, we're going to go to positive infinity. What about around x equals to 2? So I'm going to do a little graph right here. 1, 2. All right, and same behavior. Okay, so we're gonna need this piece of information when we put everything together at the end of the exercise to graph that function. Determine horizontal asymptotes if they exist. All right, now let's go back to the previous page real quick. And for horizontal asymptotes, well, in this case, look at the degrees of the leading terms. In this case, the leading term is of the numerator is 1, and the degree of the denominator is 2. So in this case, the denominator degree is larger than that of the numerator, and that was the case in which the only so degree of denominator is less than degree of numerator. That means the only horizontal asymptote is y equals to 0. That is the x-axis. Okay, determine the oblique asymptotes if they exist. Well, we already have a horizontal asymptote. Well, there's no oblique asymptotes in this case. And the reason for that is because the condition to have oblique asymptotes is that the degree of the numerator is 1 more than that of the denominator, and well, in fact, we have the reverse. So in this case, not applicable. All right. Determine the points, if any, at which the graph of R of x intersects the horizontal or oblique asymptotes. All right. So let's see. How do we do that? So in this case, we are looking for points of intersection between the original function y equals x minus 1 over x squared minus 4 and y equals to 0, which is the equation of the horizontal asymptote. So we need, in other words, what we need is to set these two quantities equal to each other and solve the equation. X minus 1 divided by x squared minus 4. And we already solved this equation. We already did it, but the purpose of doing this, solving the equation, was nothing other than getting the x-intercept. Okay, so I'm going to multiply both sides by x squared minus 4. Okay, and then, so in this case, these two guys here cancel, and 0 times that quantity is going to be just a 0. So I get x minus 1 equals to 0, so x equals 1. So these two intersect at x equals 1. All right. So, and what's the point? The y value is simply 1, 0. All right. So let's move on to the next section. Use the real zeros of the numerator and the denominator of R to divide the x-axis into intervals. Determine where the graph of R of x is above or below the x-axis by choosing a number in each interval and evaluating R of x there. Okay, so we know that the zeros of all of the zeros, numerators and denominators, one of them is x equals 1. That's the numerators, and the denominators are x equals -2 and x equals 2. So those are the zeros of numerator, and these two for the denominator. So I'm going to draw a number line here. And I'm going to write these zeros from smaller to larger. -2, 1, and +2. Okay? And I'm going to, let's describe every single interval. So the first interval, it's going to be negative infinity to negative 2, negative 2 to 1, and 1 to 2, and then 2 to infinity. We're going to choose a number within each of the intervals. I'm going to choose the number, how about the number 3? Negative 3 rather. Negative 3 between negative 2 and 1. I'm going to choose the number 0 between 1 and 2. I'm going to choose, well, 3 halves, which is 1.5. Okay. And between 2 and infinity, or larger than 2, just 3. Okay. So we are going to find the value of r of x. In other words, all we do is plug in these numbers in the original function. So r of negative 3, and using a calculator you should get negative 0.8. I'm going to skip this part because I don't want to take a lot of time doing these calculations. Just use your calculator or do it by hand. And r of 0 equals, I get 1/4 or 0.25. Decimals are okay here. This is just to get an idea of the position of the graph at different points. And then r evaluated at 1.5. I get, where's my calculator? Because first I got a fraction. So let me change that to a decimal. That's a negative 2/7. That's a negative 0.29. And r of 3 equals 0.4. Okay. Now location on the graph. How do we get the location of the graph? Well, based on the sign, because this number, this y value is negative. This is below x-axis. Because this is positive, this is above x-axis. Because this is negative, this is below x-axis. And because this is positive, this is above the x-axis. All right. Now, what is the point on the graph? Well, convert this function notation into order pairs. That is negative 3, comma negative 0.8, 0, comma 0.25, 1.5, comma negative 0.29, and 3, comma 0.4. So those are the order pairs, the points that we want as extra. All right, so now we're going to use the result from the previous steps to graph r of x, to graph the given function. So first of all, what are the pieces of information that we have? Keep in mind that we had 2 vertical asymptotes. Those vertical asymptotes, I will paint them with red. So one of them is x equals negative 2. The other one is x equals positive 2. I need something straight to draw these lines. Well, I'll try my best. And so at x equals negative 2, I'm going to have this vertical asymptote. At x equals positive 2, I'm going to have another vertical asymptote. And we also have a horizontal asymptote, which is y equals 0, or the x-axis. Okay, what other pieces of information do we have? Well, let's go back maybe to the first page. The intercepts. One of the x-intercepts was x equals 1. So x equals 1 was the x-intercept. And the y-intercept equals 1/4, which is the same as 0.25. Well, if we divide this by half, well, half of the half will be this point right there. All right, anything else? Let's see, other points that we got from the graph. Let's see what other pieces of information. Oh, behavior around any X intercept. So keep in mind that at x equals 1 crosses the x-axis in the form of a line with a negative slope. That is something like this. And it makes sense with the behavior here, right? Because it should cross this way. Anything else that we have from here? I believe we did, we also had additional points. The additional points that we got from this function, right? From this, calculations. So we got that -3, -0.8, which is almost 1. That's 1 point. And then what else? 0.25, we already got this one, is the Y-intercept. 1.5, which is right in the middle here, and then this point there. And 3, 0.4, almost a half, somewhere here. All right, this is just a bunch of points. However, remember the behavior around the asymptotes. About the first asymptote, we go to -infinity on the one side and +infinity on the other. So we should have this sort of behavior around x equals -2. Around x equals 2, we are going to have this behavior right there. And that behavior over here. Whoops. So this is going to be enough information to draw the graph of the function. So I'm going to keep going over here. That's one part. The second part will be like this. And let me keep going over here. Okay, and last but not least, okay, it's going to look like this. All right. So, of course, you might want to use your graphing calculator to verify this result. My graph is not perfect, but it's going to have essentially the same, the same shape. Okay, let's do another example. We have another rational function, f of r of x equals x squared minus 1 divided by x. If needed, write it as a single rational expression that's already given. Then factor numerator and denominator of r of x. So in this case, only thing we need to factor is the numerator, which is going to be x plus 1 times x minus 1 divided by x. To find the domain, well, keep in mind that it is only the denominator what's causing trouble here. So let's highlight this guy here, the denominator x, and set it equal to 0. So x cannot be 0. The graph, exclude the values. Exclude that hole, that open bubble, using interval notation, -infinity to 0 union, 0 to +infinity. And what else we have? Set notation x such that x cannot be 0. Right? So that's the domain. Let's move on to the next page to keep moving with this exercise. Write r of x in lowest terms if applicable. It's not applicable in this case because there's no common factor that divides out. We will get one of those, you will see, and that's going to give rise to holes. Well, I don't want to move on too quickly, so you'll see when we get there. Find the intercept. So X intercepts and Y intercepts. X intercepts, recall that to find the X intercepts, X minus 1, X plus 1 over X. Set it equal to 0, set the function equal to 0 and solve for X. If we try to solve this for X, cancel this X's, 0 times X is 0. X minus 1 times X plus 1 equals 0. So that X intercepts are X equals 1 and X equals negative 1. Again, the intercepts should be expressed as order pairs. However, our textbook and the homework system writes intercepts as order pairs, not, as values only, not order pairs. All right. Now let's find Y-intercept. Y-intercept. Let me write down the function again. I'm going to go with the original function. Why not? Either way is fine. X squared minus 1 divided by X, which is our original function. So in order to get that, replace X with 0 and simplify. However, look at what's going to happen here. So when I plug in 0 here, I'm going to get a 0 in the denominator. That is, in this case, first of all, 0 squared, which is 0. 0 minus 1 divided by 0, that is negative 1 over 0, which is undefined. So that means there is no Y-intercept. Okay, determine the behavior of the graph of R at any intercept. So keep in mind that we have two X intercepts. One of them is at around X equals, near X equals negative 1, from smaller to large. Again, we plug in R of X. We plug in X equals to negative 1 at all factors except at the one that makes it 0. So that is, that's going to be negative 1 minus 1 times X plus 1. We leave the X over here and divide that by negative 1. So negative 1, negative 1. So what are we going to have? Negative 1 minus 1, that's going to be negative 2. Negative 2 times X plus 1 divided by negative 1. Negative 2 divided by negative 1. That gives me positive 2 times X plus 1. If we distribute, we get 2X plus 2. So in this case, the graph will cross the x-axis at X equals to negative 1 in the form of a diagonal line, of a straight line with a positive slope. Now let's find out what's going to happen around X equals positive 1, the other X intercept. Okay, so we are going to do the same, plug in X equals 1, except at the first factor that actually makes the numerator 0. So R of X will be X minus 1 times 1 plus 1 divided by 1. Okay, so what are we going to have? 2 plus 1 equals 2. Okay, 2 plus 1 equals 2. 1 plus 1 equals 2. And divided by 1, it's going to be 2 simply. And what are we going to have here? Divide that by 1. Well, 2 times X minus 1. Simplify or distribute the 2. So in this case, we're also going to have the behavior of a straight line crossing the x-axis with a positive slope. That is, the graph is going to go from below the x-axis to above the x-axis. It's the same way here. It's going to go from below the x-axis to above the x-axis. As opposed to the previous example, if you recall, we got this negative 1/3 x plus 1/3. In this case, it went from positive to negative. And if you observe the graph, of that function, just so you can see the contrast here. It went from positive to negative. So we're going to have the reverse in this case. Alright, so determine the vertical asymptotes and holds if they exist. So again, let me write down the function r of x equals the factor form of it, x minus 1 times x plus 1 divided by x. So the only source of information for asymptotes again is the denominator. Highlight the denominator, and that's going to give us that the vertical asymptote is x equals to 0. That is the y-axis. Determine the behavior of the graph on either side of any vertical asymptote. So, well, there's only one vertical asymptote, so around x equals 0, so we are going to have the following. Let me draw the graph right here real quick. And in this case, well, notice the power of the denominator is odd. So in this case, let me draw the vertical asymptote. So it's going to look like this. Approaching 0 from the left, we go to negative infinity. However, approaching from the right, we go to positive infinity. So that's the behavior around. Determine the horizontal asymptote if they exist. So in this case, there is no, well, horizontal asymptotes. There are no horizontal asymptotes because, so in this case, we are going to have an oblique asymptote because in this case, I'll show you why. So not applicable, no horizontal asymptote. But in this case, if you look at the degree of the numerator, again, let me write this as x squared minus 1 over x. The degree of the numerator is 1 more than the degree of the denominator. So that means we will have to do polynomial long division and find the equation of the oblique asymptote. So in this case, x squared plus 0x, let me put the placeholder, and then divide by x. Alright, so x squared divided by x, I get simply x times x, that's x squared, change the sign, and that's, well, we're done. Plus 0x minus 1, boom, let's do the balance here. Cancel, 0 plus 0 is 0x. Oh, actually, oops, we don't need. And then minus 1. So this is written in the form of x plus, that's a 0x, we don't need to write anything, x plus negative 1 over x. So the oblique asymptote will be of the form y equals to x. It's going to be the diagonal line that passes through the origin. Alright, let's move on to the next page. Determine the points, if any, at which the graph of r of x intersects the horizontal or oblique asymptote. So, well, in this case, there is no horizontal asymptote. Okay? And in this case, the oblique asymptote, it's not going to be, the graph is not going to intersect the horizontal asymptote. Well, so in this case, we're looking, maybe I should have left more space here. I'm going to use the back of the page if I need. So we look for the intersection between y equals the original function x squared minus 1 over x and the oblique asymptote. Well, there's no horizontal asymptote, but there is an oblique asymptote, which is y equals x. So I'm going to use the back side of the page, well, of the previous page, right, so you can still see what we're doing here. So I'm going to set these two guys equal to each other. That is x squared minus 1 divided by x equals x, and I'm going to solve this equation for x. So I'm going to multiply both sides by x to get them canceled from the left hand side. Then x times x is going to give me x squared and x squared minus 1 will remain on the left hand side. Now the goal here is to have x's on the left and constants on the right. So, but something weird is going to happen here. Do you see what's going on? So x squared minus x squared cancels, negative 1 and equals 0. In this case we get one of those some weird things here. So because this equation has no solution, then the function and its oblique asymptote do not intersect at all. Okay, so let's move on. Let's use the real zeros of the numerator and denominator to divide x into the x-axis into intervals, blah blah blah. So we're gonna do the same as we did on the previous example. So this is what we do. So let's list the zeros. The zeros actually are x equals to negative 1 and x equals 1 from the numerator, and the 0 from the denominator was x equals 0. So I'm going to list them from smaller to large. Negative 1, 0, and 1. So this will give rise to the following interval: negative infinity to negative 1, negative 1 to 0, 0 to 1, 1 to 0. Okay, so I'm going to choose a number. I'm going to choose, well, not just random numbers that are within the interval. So I'm going to choose negative 2 over here. Between negative 1 and 0, well, there's no integer in between, so I'm going to use negative 0.5. Same over here, but positive 0.5 and positive 2 over here. What do we have to do? Evaluate at the original function at each of these 4 values of x that we chose. R of negative 0.5, R of 0.5, and R of 2. And to avoid wasting a lot of time doing these calculations, I had them for you. This is negative 1.5, this is 1.5, this is negative 1.5, and this is 1.5. That means because of the negative, this is below the x-axis. Because this is positive, this value, y value is positive, the graph of the function is above the x-axis. And over here, another negative number above the x-axis. Oh wait, no, not above, rather below. And again above. And that's it. So the points on the graph are going to be negative 2, negative 1.5. The point is going to be negative 0.5, 1.5. The point is going to be 0.5, negative 1.5, and 2, 1.5. Typically we don't use decimals, right? However, in this case we're taking a break of those we're looking function, rather numbers, not functions, because when it comes to graphing, we need those decimals to have a good estimate of what we are obtaining here. All right, let's use all the information to graph this the given function. So number 1, we have a vertical asymptote at x equals 0. That is the y-axis itself. And then we have a diagonal or oblique asymptote, which is of this form. It's one of these weird looking type of asymptotes. And then now let's see. Do we have x intercepts? Well, yes, we have as an x intercept x equals to negative 1 and x equals 1. Again, recall that we do not have any y-intercepts. Okay, and what else do we know? So we know that the graph crosses the x-axis from the previous page. It was at the previous page. 3 and 4. Oh yes, that's the previous page. At x equal around or near -1, it crosses in the form of a positive. It goes from negative to positive, from negative to positive. Okay, so it's going to do something like this, and same over here, it's going to do something like that. Now let's look for the other points. So in this case, we use the point, we chose the point -2, -1.5. So -2, -1.5, which is around here, and then the point -0.5 comma 1.5. So that's something somewhere over here, and then 0.5 comma -1.5, and 2 comma 1.5. So let's trace, let's actually connect the dots. Okay, so this is roughly the graph. Let's just continue asymptotically, you know, these are never going to touch. Right, and that's going to be the graph of the given function. All right, let's look at another example. So let's see. Given the rational function, let's do the same. Well, for x to the 4 plus 1 divided by x squared. So in this case, letter A, we can just skip. There's actually nothing to factor out because we have a sum of perfect squares. So let's see, find the domain. So let's just not applicable. Just write that down. Find the domain. So the domain, it's going to come from the factors of the denominator, or the values of x that make the denominator 0, and in this case x cannot be 0. Again, use the same approach, -infinity to 0, union 0 to positive infinity. That's one notation in interval notation. Again, the ones I'm shading are the okay inputs to the function, except 0 itself. And using interval set notation, we express it at x such that x cannot be 0. Write r in the lowest point, in lowest terms if applicable. So in this case, well, not applicable. Nothing divides out. There's nothing that we can factor out. Find the intercepts, x intercepts. For the x-intercept, set x to the 4th plus 1 divided by x squared equals to 0, and solve the equation for x. So in this case, multiply both sides by x squared to get x to the 4th power plus 1 equals to 0, and x to the 4th equals to -1, and in this case, to get rid of the 4th power, we need to take the 4th root on both sides. However, even indices with negative radicands have no solutions here. Hence, no x-intercept. Let's look at the Y-intercept. For the Y-intercept, evaluate the original function at x equals to 0. That is, plug in 0 for x, and look what's going to happen. So 0 to the 4, which is still 0, plus 1 over 0 squared, which is 0. That is 1 over 0, which is undefined. For that reason, there's no y-intercept either. No X-intercepts, no Y-intercepts. All right, yes, I mean, functions like this are very common actually. So, determine the behavior of the graph of R of X at any intercept. So in this case, well, not applicable because there's no intercepts. Determine the vertical asymptotes and holes if they exist. Again, keep in mind that, okay, let me write down the function R of X, x to the fourth power plus 1 over x squared. The vertical asymptotes come from the denominator, just the same as the domain. So that means x equals 0 is the vertical asymptote. But one thing worth noting here is that the asymptote is of multiplicity 2. And that's going to change the whole game when it comes to determine the behavior of the graph on either side of the vertical asymptote. Remember what we did earlier? I wrote the function R of X equals 1 over x squared times x to the 4 plus 1. This is equivalent to say x to the 4 plus 1 divided by x squared. Okay? Those are equivalent expressions. Now, what we have to analyze here is this portion. So, near or around x equals 0, we are going to have, remember what we have when we, how does the graph look like when we have an even power? From either side is going to have this shape. So we can anticipate that the final shape of the graph that we want to do, the plot that we want to do is going to have some sort of this behavior around this asymptote. Determine the horizontal asymptotes if they exist. Well, in this case, there is no horizontal asymptote because the degree of the numerator differs by 2 or more. So in this case, we are going to have some sort of an oblique asymptote. I mean, this is going to be oblique with quotation marks. I will explain why. So I'm going to do the division, x to the 4 power plus 1. I'm not going to add placeholders. There will be too many, and we're not going to need them. Trust me. X squared. So x to the 4th divided by x squared. I'm going to get x squared. Then x squared plus x squared times x squared. That's going to be x to the 4th with opposite sign. These guys cancel. The remainder is 1. So the oblique asymptote will be y equals x squared. So we're going to have a parabola, a dashed parabola. You will see how this one is going to look like. All right. So let's move on to the next page. What do we have? Determine the points, if any, at which the graph of R of X intersects the horizontal or oblique. Well, there's no horizontal asymptote, but there's oblique asymptote, and again, I don't have enough space. I'm going to use the back side of this page to, so we want the intersection between the function y equals x to the 4th plus 1 over x squared and the oblique-ish asymptote, or rather the parabolic asymptote. That's a more proper name. So let's set these two expressions equal to each other and solve the equation for x. So when I multiply both sides by x squared, I get x to the 4th plus 1 equals x to the 4th, and look what's going to happen here. 1 equals to the 0. So, well, that's a false statement. For this reason, no intersection. All right. Now let's use the real zeros of the numerator and denominator. Okay, so the numerator, no zeros. However, the denominator, the only one zero was x equals to 0. So I'm going to choose a number in between and before and after 0. This will give rise to the interval negative infinity to 0, 0 to infinity. And I'm going to choose a number. I'm going to choose negative 1. I'm going to choose 1. And then we are going to evaluate the original function at these values that we actually positive 1, negative 1. Okay, and when I plug in negative 1 at the original function, I get to again use the calculator or do it by hand. I don't want to spend too much time on this, otherwise the video would be too lengthy. And then location on the graph of will be, because both values right here are positive, both are above the x-axis. Same here, above x-axis. The point of the graph will be negative 1, 2 and positive 1, 2. Okay, so now we have all the information to graph this function. So I'm going to start with the vertical asymptote. The vertical asymptote is actually the y-axis itself. All right, now let's see. The other asymptote that we got from the previous step, the previous page, was something that looks like a parabola. So this is what I'm going to do. I'm going to plot the points on the graph of y equals x squared, 1, 1, 2, 4, 3, well, 9. It's not going to have enough space. Negative 1, 1, negative 2, 2, negative 2, 4, not negative 2, 2, never mind. Let me erase that point so it doesn't interfere here. And instead of drawing a solid parabola, I'm going to draw a dash parabola. It's going to look an asymptotic parabola. This is one of those weird cases, very special cases that we need to also be familiar with, so when we look at something like this, doesn't feel like what to do in this situation, how to deal with them. Okay, so what else do we have? Well, X intercepts, Y intercepts, there's none of them, remember, from the previous page. So no X intercepts, no Y intercepts. However, the only piece of information that we have was these additional points. Negative 1, 2. Negative 1, 2 is 1 point. 1, 2. All right. What other piece of information do we have here? All right. Let's see. What if we use the information around the information about the behavior near x equals 0? It goes up to positive infinity in either case. So something like this. And of course, this graph, okay, this is what I'm going to do. Something like this. And then go closer to the asymptote, but never actually touching it. Same on that side as well. All right, and that's going to be the graph of the function. So, of course, if you graph this function, let me actually do it for you. Let's y equals, okay, let me clear, open parentheses, x to the fourth plus 1 divided by x squared. See how it looks like that? Except that, again, your graphing calculator is not going to display asymptotes, right? Let's move on to the next example. So we're going to have the rational function r of x equals 3x squared minus 3x divided by x squared plus x minus 12. First step is to write the given function as a single rational expression. We already got that. And factor both numerator and denominator. So writing this in factor form, we can factor out 3x times x minus 1 and divided by factors of negative 12 that add up to positive 1. That's going to be x plus 4 times x minus 3. So let's see. So, well, let's keep it like that, but there's nothing else to do any further. The domain, again, the domain, it's the information to obtain the domain of the function, it's going to come from the denominator. Those factors of the function that make the denominator 0, like x plus 4, set it equal to 0. That means x cannot be negative 4, x minus 3, x equals positive 3 actually. So let's plot these numbers on the number line, negative 4 and 3. So let's see, using interval notation, negative infinity to negative 4, union negative 4 to 3, and union 3 to positive infinity. All right. And using interval notation, set notation, x such that x cannot be negative 4, 3. So those are the numbers that are excluded from the domain. Write r of x in lowest terms if applicable. Well, in this case, not applicable. There's no common factors that divide out. Again, those are going to come soon. Actually, I think it's going to be the next example. Find the intercepts, x intercepts and y intercepts. So x intercepts, set the function equal to 0 and solve the equation for x. All right, so let's see what this is about. So first of all, let's multiply both sides by x plus 3, x plus 4 rather, x minus 3, x plus 4, x minus 3. This one came up a little bit lousy here. Let me fix everything here. So this will be x plus 4. All right, and over here everything cancels out. And I'm going to get 0 times quantity, which is going to be just 0. 3x times x minus 1 equal to 0. Well, it's already factored for us, so this is really nice. So from here, x equals 0, and from there, x equals 1. So those are the two x intercepts. What about the y intercepts? So for y-intercept, all we do is plug in 0 for the original function. I'm going to use the unfactored one actually. That's equals r of 0. That's a 3 times 0 squared minus 3 times 0 divided by 0 squared plus 0 minus 12. So let's write down the 0 there where it corresponds. That's precisely x. Okay, so what are we going to obtain? So 0 squared, that's 0 times 3, that's a 0. So 0 minus 3 times 0, which is 0. And then 0 squared is 0 plus 0, which is 0 minus 12. So that means 0 over negative 12, which is 0 is the y-intercept. Okay? So in fact, if you can tell here, it's going to cross or pass through the origin. Determine the behavior of the graph around all of the intercepts. So near x equals 0, we get r of x behaving the following way. So we get again, we don't evaluate the function at x equals 0 because it's going to zero it out. 3x times 0 minus 1 divided by 0 plus 4 times 0 minus 3. Let's write down those zeros. I'm going to use same color, why not? So 0 plus 4 is 4. 0 minus 3 is negative 3. Okay, so 3x 0 minus 1, that's a negative 1. This is 4 times negative 3. Look what's going to happen. 3 times the negative 1 cancels with this negative 3. And what we obtain is 1/4 of x, which is a diagonal line with positive slope. Now near x equals to 1, r of x will behave approximately like 3 times 1. In this case, we plug in 1 over here, but not here, because otherwise it makes it 0 and we don't get any information. So that's a 1 plus 4, and that's a 1 minus 3. So this is going to be 1 plus 4 is 5, 1 minus 3 is 2, 5 times 2 is 10, 3 over 10 times x minus 1, which is 3 over 10 x minus 3 over 10. That means, again, the behavior around or near x equals 1 will be that of a diagonal line going from negative to positive. Alright, determine the vertical asymptotes and holes if they exist. Again, vertical asymptotes come from the denominator, just the same as the domain. Let me write the whole function again in factor form. So the vertical asymptotes, this is going to be x equals negative 4, and the other one will be x equals to 3. Alright. Determine the behavior of the graph on either side of the vertical asymptote, of any vertical asymptote. So that's where we are going to write the function in a slightly different way. So r of x, it's the same as saying 1 over x plus 4, 1 over x minus 3 times 3x times x minus 1. So around x equals negative 4 and around x equals to 3, we're going to have two asymptotes. One of them is negative 1, negative 2, negative 3, negative 4. And the multiplicity of this guy is 1, which is odd. So that means we're going to have something looking like this. And around x equals 3, 1, 2, 3, boom, 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 asymptote. And like that. So around x equals to negative 4. Coming from the left, we go down to negative infinity. Coming from the right, we go up to positive infinity. Around the vertical asymptote x equals to 3. Coming from the left, we go to negative infinity. And coming from the right, we go towards positive infinity. let's see what's next. Determine the horizontal asymptotes if they exist. So in this case, horizontal asymptotes. Let's go back to the original problem. Let me write it down. So that's r of x equals 3x squared minus 3x divided by x squared plus x minus 12. Alright, so in this case, if you guys observe the degrees of the numerator and the denominators match, when those degree of numerator is the same as degree of the denominator, that means the horizontal asymptote will be the ratio of a sub n, which is the leading coefficient of the numerator, and b sub m, which is the leading coefficient of the denominator. So that's the key in this case. So the horizontal asymptote for our case will be 3 over 1, which is the same as y equals to 3. That's our horizontal asymptote. Oblique asymptotes, well, there won't be oblique asymptotes because we have already a horizontal asymptote, so not applicable in this case. Determine the points, if any, at which the graph of r of x intersects the horizontal or oblique asymptotes. In this case, the horizontal asymptote. So need intersection between the original function of 3x y equals 3x squared minus 3x divided by x squared plus x minus 12 and y equals 3, which is the asymptote. So let's set these two quantities equal to each other. So 3x squared minus 3x, and at the beginning it's going to look really ugly, but it's not going to be as bad as it's looking already. Set that equals to 3, which is the same as saying 3 over 1. So you can multiply both sides by the denominator, or simply do some cross multiplication. I think that's shorter to write. So this remains 3x squared minus 3x equals 3 times x squared plus x minus 12. I know what you'll be thinking here. Well, it's going to look really ugly because we will have to distribute, but no, we're not going to distribute. In fact, notice this 3 and that 3 over there. I'm going to factor out the 3 only. 3x squared minus x divided by 3, x squared plus x minus 12. So I'm going to divide both sides by 3. Notice how they are going to cancel there. So we're going to get x squared minus x equals x squared plus x minus 12. Again, because we're solving an equation, our goal is to have all the x's on the left hand side and pure numbers on the right hand side. So I'm going to subtract x squared and subtract x. And that it's going to be really relieving to know that the quadratic terms are going to go away. Otherwise, we would have to use some quadratic method to solve the equation, either factoring or quadratic formula. Anyway, it's not the case. So we're left with negative x minus x, negative 2x equals to negative 12. All we do is divide both sides by negative 2 to get x equals 6. So at x equals 6, it is the original function intersecting with the horizontal asymptote. So the point is x comma 6. I mean the point 6 comma y equals 3 at that point, which is going to be one of the pieces of information that we're going to need in order to graph that function. So use the real zeros of the numerator and denominator to divide the x-axis or the number line into intervals and test. For the numerator, the zeros where x equals to 0 and x equals to 1. For the denominator, the zeros where x equals to what they were? They were -4 and x equals to 3. Okay. Now let's do this. Let's plot the numbers from smaller to large. Alright, so the largest of them is -4, and then followed by 0, then by 1, then by 3, and then, well, there's supposed to be just an arrow here. Alright, so what are we gonna have? 1, 2, 3, 4, 5 regions to test. So the first interval is gonna be -infinity to -4, -4 to 0, 0 to 1, 1 to 3, 3 to infinity. Alright, now let's choose a number, our favorite number here, I guess. That's going to be -5, between -4 and 0, -1. Well, actually, I'm going to choose -2, not -1. Alright, just because. And then between 0 and 1, I'm going to choose 1/2 or 0.5. Again, decimals are okay here, just to have an idea of the positivity or negativity of the number. And then between 1 and 3, I'm going to choose 2. Well, that's the only possible integer. And between 3 and infinity, I'm going to choose 4. Now let's evaluate the original function at these 1, 2, 3, 4, 5 numbers. R of -5, that's going to be equal R of -2, R of 0.5, R of 2, R of 4. Alright, now so when I plug in -5, I get 11.5. Well, 11.25, right? Actually, not 5. 11.25. R of -2, I get -1.8. R of 1/2 or 0.5, I get initially I got 1/15, but I'm gonna choose this 1 over. I'm gonna choose 0. I'm gonna use decimals, 0.07. That's a really tiny number. And what else? R of 2, I get -1, and 4.5 when I plug in 4. Okay. Location on the graph, because it's positive, this is above x-axis, below, above, below, and above again. Okay, x-axis, 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 x-axis. All right. Point of the graph, just write these guys in the form of ordered pairs. -5, 11.25, -2, -1.8, 0.5, 0.07, and 2, -1, and 4, 4.5. And we already have all the information to graph. So this graph is going to be huge in space. Well, so let's start with, let's see. I'm going to start with the vertical asymptotes first. So for the vertical asymptotes, we had, where are they? Vertical asymptotes, -4 and +3. So I'm going to go towards a -4 and +3. Okay, let me draw the rest of the asymptotes. Okay, this one gonna take a good minute to draw. Do we have any horizontal asymptotes? If I remember that well, yes. We had one right there. Y equals to 3, a horizontal line, horizontal asymptote. That's going to be over here. What else do we have? Intercepts, X intercepts and Y intercept. So X intercept is 0 and 1, and Y intercept is Y equals to 0. So X intercept is so this one is gonna be a little bit tight to draw, actually. And then other points on the graph. All right. Well, actually, behavior, which we get from the asymptotic behavior right here around x equals to -4. It's gonna go into different infinities, negative on to this end, something like this, and something like that over here. All right. Around the other asymptotes, same. In this case, we are gonna have hold on. We're gonna have something like this. And something like that over here. All right. Let's plot the other points. Okay, let's plot in the other points. We get the additional points. So we got -5, 11.25. So -5, 11. Well, should have gone over here. Well, never mind. That's gonna be 11.25. So let me erase this part of the graph. I'm gonna make it a little better. All right, and let me fix this asymptote here. And then I got -2 point, -1.8, -2, -1.8, pretty much -2, but not quite. And then 0.5, that was the point I graphed. And then 0.5, 0.07, basically, so halfway, basically here, if you will. And then did I get anything else? 2, -1, 2, -1, and 4, 4.5, which is right here. All right. And the graph must have the following behavior. It's going to look something like this. Right, it's not perfect over here. Over there should look like falling here. And over there on the other side, it should look like this, right? Again, it's not, this grid is, due to the size of the grid, it's not easy to come up with the perfect graph right here, right? And what else do we have? I think that's about it. That's about it for this function. Now let's look at another example. The next one, let's see. Let me just organize my pages here. 8, 9, 10. All right. So for the function 2x squared minus 5x plus 2 divided by x squared minus 4. All right. So if necessary, write it as a single fraction. Well, it's already as a single fraction. Then factor the numerator. So we need to factor the numerator and the denominator. So when we write this using factoring r of x, the denominator will be x plus 2 and x minus 2. And the numerator, for the numerator, well, I don't want to spend too much time doing the factoring. I'm just going to give you the factors. 2x minus 1 times x minus 2. All right? So how do we get the factoring of this? Well, you might want to use the diamond method or guess and check, which is methods that we have covered in a review session earlier. All right, so find the domain of r of x. And I know what you're thinking. You might want to cancel this. Not yet. So the domain of this function will be obtained from the factors that make the denominator 0. That is x plus 2 equals the 0 and x minus 2 equals the 0. That means x cannot be negative 2, x cannot be 2. Using the bubble approach as usual, the function is defined for all values, for all the real numbers except those that have the open circle, the open bubble. That is negative 2 and 2. So negative infinity, comma, negative 2, union negative 2 to 2, union 2 to positive infinity. And then using set notation x such that x cannot be negative 2 and 2. Write r of x in lowest terms if applicable. That's what we do now. Divide out this common factor, so we get 2x minus 1 over x plus 2. Find the intercept. So again, to find the x-intercept, set the function equal to 0 and solve for x. So multiply both sides by x plus 2. Cancel the x plus 2, 0 times x plus 2, it's going to give us still a 0 and then 2x minus 1. Solving this equation for x, we get x equals 1/2. So that's the x-intercept. For the y-intercept, we're going to plug in 0 wherever we see the letter x. So 2 times 0, which is 0 minus 1, that's a negative 1. 0 plus 2, that's 2, so we get negative 1/2. Okay, so those are the intercepts. Okay, so now let's see. Determine the behavior of the graph ABBA at any intercepts. In this case, the x-intercept, so near near 1/2. Well, actually, let me keep it as 1/2. We are going to do r of x, which is approximately 2x. We don't put the 1/2 over here because otherwise it makes our denominator equal to 0. And so 2x minus 1 divided by x plus 2, but in this case that plus 2 is going to be with 1/2. So 1/2 plus 2 is going to give us 2 times 2, that's 4 plus 1, which equals 5/2. Dividing by a fraction is the same as multiplying by the reciprocal, 2/5 times 2x minus 1, which is, distributing this, we get 2 times 2, that's 4/5 x minus 2/5. In other words, this is going to behave like a line crossing the x-axis, going from negative to positive in this direction. Determine the vertical asymptotes and holes if they exist. So this is finally one of those examples in which we are going to have both of them. So let me write down the one fully factor without dividing out any common factor. So 2x minus 1 times x minus 2. I'm going to write it again. It's on the top of this page, but to avoid scrolling, moving through the pages, x plus 2 times x minus 2. Okay, so notice how these are the same. All right, because of this cancellation, whole at x equals positive 2. How do we find the y value? We plug in x equals to 2 in the reduced form. We're going to do that afterwards. However, we still need to state the location of the vertical asymptote. At x equals to 2. So x equals to actually negative 2. I need to write that down, that negative. X equals to negative 2. Okay, so I need to find the y value of the whole r of x equals 2x minus 1, x plus 2. So let's evaluate. Let's evaluate that at 2. What are we going to get here? So 2 times 2, which is 4, minus 1, that's a 3. And 2 plus 2, which is 4. 3/4, which is 0.75. Okay, we're going to need that in decimal. Alright, let's move on to the next part of this. Determine the behavior around on either side of any vertical asymptote. So we have the vertical asymptote x equals negative 2. And notice the order of the vertical asymptote x equals negative 2. It's order 1. So it's going to look like this. All right, it's going to look like that. Now, let's see. Determine the horizontal asymptotes if they exist. For that, I'm going to refer to the original form without any factoring, 2x squared minus 5x plus 2 over x squared minus 4. So in this case, let's see. Observe that the degrees of the numerator and the denominator match. So in this case is that form in which y equals a sub n divided by b sub m, where n is the location of the leading term and m is the location of the leading term of the denominator in this case. So the ratio will be obtained as 2 divided by 1, which is 2. So y equals 2 will be the horizontal asymptote. Oblique asymptotes, well, not applicable in this case because we already have a horizontal one. Determine the points, if any, at which the graph of R of x intersects the horizontal or oblique asymptote. So in this case, need intersection between. In this case, I'm going to use the function in its simplified form, not the one with all factors. In this case, in order to save a lot of the work. So I'm going to get 2x minus 1 over x plus 2, and the horizontal asymptote y equals to 2. In other words, we need to set 2x minus 1 over x plus 2, set it equal to 2. This is the same as 2 over 1. We might want to use cross multiplication to simplify calculation. 2x minus 1 times 1 is 2x minus 1, and 2 times x plus 2. Distributing this, we get 2x plus 4 and 2x minus 1 on the left hand side. Subtracting 2x on both sides, we get negative 1 equals to 4, which is an impossibility in this case. This is no solution, so no intersection. Use the real zeros of the numerator and denominator of R of x to divide x into intervals. So the zeros of the numerator where in this case, well, negative 2, one of the other 0 was 1/2, and the removable, the one that was the whole was positive 2, so we consider that as well. So the intervals are going to be negative infinity to negative 2, negative 2 to 1/2, 1/2 to 2, and 2 to infinity. Okay, let's choose a number. The numbers that I will choose in this case are negative 3, negative 1, 1, and 3. So we are going to evaluate the original function at these values of x. So r of negative 3, r of negative 1, r of 1, r of 3. So let's see, okay, according to my calculations, again, I'm not going to spend too much time on this. I get 7, negative 3, 1/3, and 1. All right. So because of the positive sign, this is going to be above the x-axis. Negative sign, that means it's going to be below the x-axis, then above the x-axis again, and again above x-axis. What are the point of the graph? So just rewrite this in form of ordered pairs. I'm going to write the 1/3 as a decimal, 0.33, blah, 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 infinitely many decimals, and 3, 1. All right, so moving on to the next page, we are going to use the results from here to graph that function. function. This one is going to be a rather interesting one. So let's start first of all with the asymptote. So we have a vertical asymptote at -2. Let's draw the graph of that asymptote. And we have a horizontal asymptote at y equals to 2. What else? So let's see. Oh, we have a hole here, remember? For the hole, which is the order pair 2, 0.75. Let's locate that point. So 2, 0.75. Well, if we divide this into fourths, or into quarters, it's gonna go around here. That's where the hole is going to be at, roughly. And what else do we have? Do we have any intercepts? Yes, we have X intercepts. Our X intercept is 1/2. So the graph is going to intercept at 1/2. Do we have any Y intercepts? Yes, we have a Y intercept, which is right there. -1/2. And then what else? Other points. Other points that are on the graph, those came from the table we did earlier here. So -3, 7. So let me plot that point. -3, let me go up to 7. And then we have the point -1, -3, -1, -3, and then the point 1, 0.33. So I'm going to go to 1, 0.33, somewhere there, and the point 3, 1, which is right there. Alright, do we have anything else? So I don't think I had any other points. So let's connect the dots right there. So not in a hole. And then over here, the behavior is gonna go like this and like that over there. Okay, let me expand the horizontal asymptote so the graph looks a little bit nicer. Okay, so that's again the graph of this function. Again, asymptotes, both the asymptotes and holes, are not going to be displayed by your graphing calculator. So that's why it's important that we follow all these steps in order to get the correct graph of a rational function. And let's do one last example and call it a day for this section. So given the rational function r of x equals 2x squared minus 8x plus 8 divided by x squared minus 8x plus 16, okay, we're gonna do the same. So, well, in this case, it's already as a single rational expression. Then we need to factor the numerator and denominator. So r of x equals, so initially I'm going to factor out the 2 in the numerator. So 2 times x squared minus 8x plus 8. Oh, actually not 8. I'm factoring out the 2. I'm supposed to be left with a 4. And then divide that by x squared minus 8x plus 16. Notice these two polynomials, these two trinomials are special because they are perfect square trinomials. All right. Let's find the domain. Find the domain. So in order to find the domain, we use the denominator, which by the way, it's going to be x minus 4. Set that equal to 0, x equals 4. So the function will take on any value of x except the one located at the hole, which is 4. So using interval notation, and using set notation, x cannot be 4. Alright? Write R of x in lowest terms if applicable. Well, in this case, nothing divides out. Okay, so not applicable. I think I left a lot of space here. Find the intercepts. Alright, let's find the intercepts. X intercept. Two times x minus 2 squared over x minus 4 quantity squared. Set that equal to 0. Multiply both sides by the denominator, x minus 4 squared, in order to get rid of it from the denominator so we can proceed and solve this equation for x. These cancel out. 0 times whatever quantity still is 0. And x minus 2 squared times 2. I'm going to divide both sides by 2 to get x minus 2 squared equals 0. But this is the same as saying x minus 2 times itself, which is no other than a repeated solution. So ultimately this is simply x equals to 2. So x equals to 2 is the x-intercept. Let's look at the y-intercept. For the y-intercept, recall that we plug in 0 in the position of x. Zero, 0, and 0. So what are we going to get here? Well, let's see. 0 minus 2 is negative 2, but negative 2 squared is going to be 4. 4 times 2 is going to be 8. 0 minus 4, that's going to be negative 4, but negative 4 squared equals 16. 8 divided by 16, that's going to be 1/2. So 1/2 will be the y-intercept. So in this case, we have both x and y-intercept. Determine the behavior of the graph around any intercept. So in this case, the x-intercept. So that means near x equals to 2. So in this case, I'm going to find an approximation for r of x. Which is 2 times x minus 2 squared divided by 2 minus 4 quantity squared. Okay, so 2 minus 4, what is that? 2 minus 4, that's a negative 2, but negative 2 squared is 4. Notice I didn't plug in 2 over here in the numerator because 2 minus 2 is going to be equal to 0, and otherwise we wouldn't get the information that we want. Squared and then divided by 4. 2 divided by 4, that's going to give me 1/2. And I'm going to expand the binomial again, x squared minus 4x, and then plus 4. And if I distribute, I'm going to get 1/2 x squared minus 2x, and then plus 2. So in other words, this around x equals 2, the graph will have the behavior of about 1/2 x squared, which is no other than a parabola. So in other words, compare this with the multiplicity of the zero. So the multiplicity of the zero is 2. The multiplicity is even. So in that case, we would expect for the graph to not cross, but actually to touch. And the behavior of a graph touching the x-axis is curvy about that point, not crossing like a straight line, like a diagonal line, either from negative to positive with positive slope or from positive to negative, which is with a negative slope. Now let's determine any vertical asymptotes and holes if they exist. So f of x, or r of x rather, which is 2 times x minus 2 squared over x minus 4 squared. So again, the vertical asymptote will come from the information in the denominator. X equal 4 will be the horizontal asymptote, no holes in this case. Because in this case, we didn't have any common factors that divide out. All right, so let's move on to the next page, second to the last page. Determine the behavior of the graph on either side of any of the vertical asymptotes, and this is where we write the function in the form 1 over x minus 4 squared times 2x minus 2 squared. So around x equals 4, which is the vertical asymptote, we are going to have the following behavior. Notice the multiplicity of 4. It's 2. So 1, 2, 3, 4. Okay, so it's going to behave basically like this. So we are going to have this behavior on the actual function after when we put all this information together. Determine any horizontal asymptotes if they exist. And in order to get this, I'm going to refer to the original form of the function r of x equals 2x squared minus 8x plus 8 divided by x squared minus 8x plus 16. And again, notice how the degrees of the numerator and the denominator match. So in this case, we're going to have, just like the previous case, the ratio of the leading coefficients, which is y equals to 2. Oblique asymptotes, we're not going to have any of those because we already have a horizontal one. And then determine the points at which r of x, which is in this case, what was I going to do? I'm going to use the original form. 2x squared minus 8x plus 8 divided by x squared minus 8x plus 16, and set it equal to whatever the horizontal asymptote is, which is 2. All right, so let's see. I'm going to cross multiply this. I'm going to cross multiply, so 2x squared minus 8x plus 8, 2 times x squared minus 8x plus 16. And I'm going to, instead of, it would take this about the same work to distribute than factoring out the 2. I'm going to factor out the 2. And then divide out the 2's. Boom, boom. X squared minus 4x plus 4 equals, boom, boom, x squared minus 8x plus 16. And I need x's on the left, numbers on the right, so I'm going to subtract x squared. Oh, nice, these are going to go away. At 8x. And I'm going to subtract 4 at the same time. So what am I going to get? I'm going to get these guys cancel. I'm going to get those guys cancel. These guys cancel. And the 4's cancel. So on the left hand side, I'm going to be left with negative 4x plus 8x. That is 4x equals to 16 minus 4. That's a 12. I'm going to write this equation over here so it looks nicer. And divide both sides by 4 simply to get x equals to 3. So the graph of the function and its horizontal asymptote intersect at the point 3, y equals 2. Okay. Use the real zeros of the numerator and denominator to divide the x-axis by choosing a number. Well, the usual here. All right, maybe I think I added too many columns here. I think I'm gonna be left with one of them because, well, the zeros in the numerator, the zero of the numerator was x equals to 2, and the zero of the denominator, it's x equals to actually positive 4. So I only need 2 and 4. I don't think I need this column at the end. So the interval in this case will be negative infinity to 2 and 2 to 4 and then 4 to infinity. And the numbers that I will choose here are going to be negative 3 and over here I'm going to choose 3, but not negative 3. Hold on, what am I doing? I'm going to just choose 0. It'll be easier. And then 5 over here. Alright, so when I plug in 0, we already got this y value, which was 1/2. So r of 0, r of 3, and r of 5. All right, so we need to evaluate this. So when I do that, I get a 1/2. Okay, that means above the x-axis because the y value is positive. When we plug in 3, that's going to be 3 minus 1. So I lost these calculations. And that's going to be, that's 2 squared, that's 4 times 2 is 8 over 1. So that's going to be 8. And that's also above x-axis. And r of 5, so 5 minus 1 is 1632, and okay, I'm gonna get a huge number, 32. I'm not going to be able to plot that value, but I'm gonna try. I'm gonna try something here anyway. Okay, so that's also above the x-axis. So the point of the graph is 0, 0.5 instead of a half, and then 3, 8, and 5, 32. All right. So we have all the information to finally have the graph of this function. Okay, number one, I'm going to start with vertical asymptote. So we have a vertical asymptote, we had 1. X equals 4. I'm going to use this purple color. Okay, and then what else do we have? Intercepts, do we have X intercepts? The X intercept is 2, the Y intercept is 1/2. Horizontal asymptotes, do we have horizontal asymptotes? Yes, we had one, that is Y equals to 2. Use the other color, Y equals to 2. And what else? Other points on the graph or intersection. Oh, the point of intersection between the horizontal asymptote and the graph, it's actually 3, 2. So the graph will pass through this point. Okay, and then we also have the behavior near the x-intercept. So the behavior near the x-intercept is that of a parabola with a stretching factor of 1/2. So it's going to be a wide parabola, something like this. And then also we have the behavior around the asymptote, which is going to be like this and like that. So both sides of the asymptote approach to positive infinity. And let's actually do that. Okay, and let's just connect the dots here. Okay, that's one part. And then this curvy, this parabola as we obtained earlier, and then I'm gonna do this and just make it go asymptotically to, well, this should have been curvy, but it was kind of hard to draw. All right, so what else do we have? We have also this side. So again, unfortunately, the point 5, 32 is not going to be possible to be plotted. So I'm just going to give you a rough sketch of the graph. Okay, and that's how it looks like. So how about we look at it on the graphing calculator, so you can see why it's not going to be kind of possible to draw. So let's see, what did we have? One, we're just going to use 2 times, what was that, x minus 2 quantities squared and divided by x minus 4 quantity squared. And you see the graph, see how it crosses at, it's very similar to this. Okay, see the point, if I trace 4.6, oh, actually I need to trace. If I go around the graph, look, when I get closer to 5 equals actually 18, not 32. I must have done a silly mistake there, but still it was kind of hard to draw this one. Okay, Alright, so this is the end of this section. So yes, it was a little bit of a long video this time because we needed to go over a bunch of examples that have, every single example I cover here had something different. Some of them had holes, some other didn't have holes, some other had some intercepts, or other didn't have intercepts, and especially this last one, I thought it was a very, actually I made it up. I thought it was good to have one in which the X-intercept is one of those with even multiplicity, in which only touches the axis, and also the behavior around the vertical asymptote is having both sides of the graph pointing towards the same end. Alright, so I think this is a good place to quit. I'll see you on the next video.